Our universe holds secrets that defy everything we think we know. Black holes warp the fabric of space and time itself, yet even they are not the deepest mystery. Today we are counting down 25 of the most baffling unexplained anomalies in space-time. These are real phenomena observed by scientists that challenge the very foundations of physics and our understanding of reality. By the end of this journey, you will have a front-row seat to the greatest unsolved puzzles of the cosmos. We will investigate why spacecraft are mysteriously slowing down and what strange force is pulling our entire galaxy towards an unseen horizon. What do you believe is waiting for us in the vast, silent dark? Two spacecraft sent to explore the outer planets began drifting off course. Pioneer 10 and Pioneer 11 were billions of miles from Earth, coasting through the silent void when a subtle and persistent mystery emerged. They were slowing down, not from hitting anything, not from solar wind, but by a tiny, unaccounted-for force, a constant sunward tug that defied all known physics. For decades, this Pioneer Anomaly baffled scientists. How could these probes, hurtling through the vacuum of space, experience a continuous deceleration so slight it was like a feather's weight pressing against them, yet so real it skewed their trajectories? The calculations were checked and rechecked. Was it the faint push of heat radiating from their own power sources, a phenomenon called thermal radiation pressure? This became the leading explanation, a simple case of the spacecraft's own warmth giving them a gentle, unexpected push. Yet for a long time, the numbers did not perfectly align, leaving a tantalizing crack in the door for something far more profound. Could this be a sign of new physics, a hint that our understanding of gravity itself was incomplete, manifesting only in the deep, quiet stretches between the worlds? This tiny anomaly proved that even the most meticulously planned journeys can be touched by the unknown. But this strange tug on distant probes is not the only speed-related mystery in our solar system. Sometimes our own planet seems to give spacecraft an unexpected and impossible push. When satellites like Galileo or Rosetta swung past Earth to steal a little of its orbital energy, a maneuver called a gravitational slingshot, something peculiar happened. Their speed after the flyby did not match the carefully calculated predictions. These were not tiny errors. They were significant, measurable jumps in velocity, as if an unseen hand had given the spacecraft an extra, gentle shove on its way out of Earth's gravitational embrace. Scientists call this the Flyby Anomaly. Every single variable was accounted for, from the planet's gravity to the subtle drag of the upper atmosphere. Yet the numbers remained stubbornly wrong. Could it be an unaccounted-for effect of our planet's rotation? A phenomenon known as frame dragging, where a massive spinning object literally twists the fabric of space-time around it. Or is the explanation something even more exotic, hidden within the complex equations of general relativity? These unplanned speed boosts are a humbling reminder that even the gravity of our own home world, a force we think we understand completely, can still hold onto a few secrets. While we grapple with strange forces acting on our spacecraft, a far greater and more pervasive mystery dominates the cosmos. Entire galaxies are spinning at impossible speeds, threatening to tear themselves apart. The outer stars of spiral galaxies orbit so fast that the known gravity from all the visible stars and gas should be utterly insufficient to hold them together. These stars should be flung into the intergalactic void, yet they remain firmly bound to their cosmic homes. This strange behavior, first mapped by astronomer Vera Rubin, is our first direct evidence for dark matter. It is as if every galaxy is embedded within a giant, invisible sphere of mass, a ghostly halo whose gravity alone keeps the stars from flying away. This unseen anchor is not the only clue. We can actually watch its gravity at work, bending the very fabric of reality. When light from a distant galaxy travels towards us, its path is warped if it passes near a massive object. This effect, called gravitational lensing, creates distorted or multiple images of the background galaxy. The amount of bending we observe often requires far more mass than we can see, revealing the hidden contours of dark matter distorting our view of the universe. So what is this mysterious substance? It cannot be ordinary matter like planets, gas, or even black holes made from stars. We would be able to detect those. The leading candidates are exotic particles that barely interact with light. Scientists call them weakly interacting massive particles, or WIMP. These hypothetical entities would pass right through our planet as if it were not even there, yet their collective gravity would shape the cosmos. Another candidate is the Action, an extremely lightweight particle born from theoretical attempts to solve other problems in physics. Decades of sensitive experiments deep underground have tried to catch a single WIMP in the act of interacting with normal matter, so far without success. The sheer scale of the mystery is staggering. Everything we can see, from the smallest insect to the largest star, makes up less than 5% of the universe. Dark matter appears to account for about 25%. We are surrounded by it, our galaxy swimming through an ocean of invisible matter, and we still have no idea what it is. This missing mass is the silent, dominant architect of the cosmic web, pulling galaxies together into clusters and sculpting the large-scale structure of everything we observe. Its nature remains one of the most profound questions in all of science. If dark matter's gravity pulls the cosmos together, a far more dominant and stranger force is actively tearing it apart. The discovery came not from looking at nearby stars, but from peering into the deepest reaches of the universe, using exploding stars as cosmic mile markers. In the late 1990s, two independent teams of astronomers were studying a specific type of stellar explosion, a supernova that always releases the same intrinsic brightness. By measuring how dim these standard candles appeared from Earth, scientists could calculate their distance and, crucially, how fast the universe was expanding when that light was emitted billions of years ago. The expectation was that the gravitational pull of all the matter in the cosmos would be slowing the expansion down, like a ball thrown upwards gradually losing speed. The data revealed the exact opposite. The distant supernovae were fainter than they should have been, meaning they were farther away. The expansion of the universe is not slowing down. It is accelerating. This was a staggering revelation that earned its discoverers the Nobel Prize. Something is actively working against gravity, pushing galaxies apart at an ever-increasing rate. Scientists named this mysterious something dark energy. The evidence for its existence is now overwhelming, woven into the very fabric of our cosmic models. Yet its nature is arguably the greatest mystery in modern physics. The leading candidate for dark energy comes from an idea Albert Einstein himself once proposed and then discarded. He called it the cosmological constant, a kind of inherent energy infused within the vacuum of space itself. This energy would have a repulsive gravity, causing empty space to push outward rather than pull inward. If this vacuum energy is real, it would mean that nothingness is not empty at all, but seething with a fundamental force that drives the cosmos apart. The numbers, however, create a problem of epic proportions. When physicists try to calculate how much of this vacuum energy there should be based on quantum theory, the value they get is impossibly large, 120 orders of magnitude too big. That is a 1 with 120 zeros after it. If that theoretical value were correct, the universe would have been ripped to shreds instantly after the Big Bang. The fact that we exist and that the observed acceleration is so comparatively gentle means our calculation of the energy of empty space is the most wrong prediction in the entire history of science. This leaves us with a truly humbling puzzle. Dark energy makes up about 70% of the entire universe. It dictates the ultimate fate of everything, and we have no real idea what it is. Will this acceleration continue forever, leading to a cold, dark, and lonely end for the cosmos? Or could this mysterious force change its behavior over time? The answer is written in the darkness between the stars, a code we have only just begun to crack. Yet for all its vastness and apparent uniformity, our universe might be subtly pointing in a specific direction. This startling possibility comes from the oldest light we can see, the cosmic microwave background. This faint glow is the remnant heat from the Big Bang, a snapshot of the infant universe when it was just 380,000 years old. According to our most fundamental cosmological principle, this background should be almost perfectly uniform in all directions. The universe on the largest scales should have no center and no edge, no preferred axis. But when scientists created a detailed map of this ancient light, they found something deeply unsettling. Certain large-scale features, like vast cold and hot spots, appear to be mysteriously aligned along a particular cosmic axis, a line that has been dramatically nicknamed the axis of evil. This alignment is not just a random pattern. It suggests the universe might have a specific orientation, a preferred direction that breaks the sacred rule of cosmological uniformity. The statistical significance of this alignment is a subject of intense debate. Is it a real feature of the cosmos, or is it just a fluke, a trick of the data? For many scientists, the hope is that it is a statistical illusion, because the alternative would force us to rewrite the very first chapters of our cosmic story. If the axis of evil is real, it challenges the core assumptions of our standard model of cosmology, the very ideas that allow us to trace the universe's history back to its first moments. It would mean that our universe is not the same in every direction after all, that our place within it might be special in some fundamental way we do not yet understand. This single, controversial line on a map of all creation serves as a profound reminder that our most basic assumptions about reality are always subject to revision by the next unexpected discovery. But the idea of a preferred cosmic direction is not just a statistical ghost in ancient light. There is a very real and powerful force pulling our entire galaxy and thousands of others toward a specific point in the cosmos. We are caught in a river of galaxies, all flowing toward a mysterious, unseen region of gravitational power known as the Great Attractor. This colossal anomaly lies roughly 250 million light-years away in the direction of the southern constellation Centaurus. Its gravity is so immense that it is dragging our Milky Way and the entire local group of galaxies toward it at a staggering speed of over 2 million kilometers per hour. For a long time, this cosmic destination was almost impossible to study. It lies directly behind the plane of our own galaxy, a region astronomers call the zone of avoidance. This area is shrouded by thick clouds of cosmic dust and countless stars from the Milky Way's galactic bulge, blocking our optical view of the universe beyond like a dense, luminous fog. It is as if the most important landmark in our intergalactic neighborhood was hidden behind a brilliant, impenetrable curtain. How do you map a gravitational monster you cannot directly see? The key was to look with different eyes. Radio, infrared, and X-ray telescopes can pierce through the obscuring dust, revealing the hidden structures behind the galactic plane. These observations have unveiled that the Great Attractor is not a single, monstrous object, but likely the heart of a colossal supercluster of galaxies, a dense knot of mass known as the Norma Cluster. Yet, even this vast concentration of visible matter does not seem to have enough gravity to account for the full scale of the pull we feel. This suggests the Great Attractor itself is just a waypoint in an even larger and more powerful cosmic flow. The true source of this motion appears to be something far grander, an inconceivably vast concentration of mass known as the Shapley supercluster, the single largest such structure in our observable universe. So our journey is not just toward the Great Attractor, but toward something beyond it, a reminder that even when we think we have found the center of the mystery, the cosmos always points to something deeper, darker, and more immense. The same silent cosmos that hides a great attractor also delivered one of the most tantalizing and brief messages we have ever received. On a hot August night in 1977, a radio telescope at Ohio State University, known as Big Ear, was automatically scanning the sky. Its printout was a long, dull column of alphanumeric characters representing the faint, meaningless hiss of empty space. Then, just after 11:16 p.m., the signal intensity surged. For 72 glorious seconds, a powerful, focused radio wave, billions of times stronger than the background noise, flooded the receiver. It was a perfect narrowband signal, precisely at the frequency of hydrogen, the most common element in the universe, a frequency many scientists had suggested would be an ideal channel for interstellar communication. The signal rose to a peak and then faded away, never to be heard again. The next day, astronomer Jerry Amon was reviewing the computer printout. He circled the string of characters representing the signal's unprecedented strength, and in the margin wrote a single, poignant word. Wow, the wow signal was born. Its origin remains one of the greatest unsolved mysteries in the search for cosmic company. It came from a region in the constellation Sagittarius with no known stars or planets at the time. Every natural explanation has fallen short. Could it have been a secret military transmission? No known human technology matched its specific frequency and behavior. Perhaps it was a reflection of a satellite or piece of space debris. The signal was fixed against the background stars, meaning the telescope's motion ruled out any object in Earth orbit. For decades, the most plausible natural theory involved comets. In 2016, a researcher proposed that two comets, which happened to be in the same area of sky in 1977, could have generated the signal by releasing large clouds of hydrogen gas. But this explanation has been widely disputed. Other astronomers pointed out that comets are not strong emitters at that specific radio frequency, and the Big Ear telescope was designed in a way that should have made it immune to such an emission. With every earthly cause cast into doubt, the extraordinary possibility remains. Was the wow signal a one-time, transient broadcast from an advanced civilization, a cosmic hello that lasted just long enough to capture our attention before vanishing back into the eternal quiet? Its 72-second duration is itself a clue. A fixed telescope like Big Ear would observe a signal from a distant point in space for exactly that long as the Earth's rotation carried the target through its field of view. Someone or something seemed to be aiming a powerful beacon directly at us. We listened for a reply for decades, scanning that same patch of sky with ever more sensitive instruments, but the silence has been absolute. The wow signal stands alone, a solitary data point in the void, a question mark written in radio waves that continues to echo across the years, challenging us to wonder if we were ever truly alone in the universe, if only for one perfect minute. While we search the cosmos for deliberate signals, some stars behave in ways that seem deliberately strange. Far from the mystery of the wow signal, a star known as KIC 8462852, or Tabby star, presents a different kind of puzzle, one written not in radio waves but in stolen light. Orbiting telescopes like Kepler are designed to find planets by spotting the tiny, regular dips in a star's brightness that occur when a world passes in front of it. But the data from Tabby's star was unlike anything astronomers had ever seen. Instead of the gentle, repeating rhythm of an orbiting planet, the star's light would sometimes plummet by enormous amounts, up to 22%, and then just as mysteriously return to normal. These were not tidy, predictable eclipses. They were chaotic, deep, and irregular, as if something vast and shapeless was drifting in front of the star, blocking its light in a pattern that defied all natural explanation. The strangeness did not end there. Long-term studies of historical photographic plates revealed that Tabby's star has also been undergoing a long-term, century-long dimming, fading by a significant amount over dozens of years. This combination of sudden, dramatic dips and a slow, steady decline made it one of the most anomalous objects ever discovered in our galaxy. The hunt for an explanation began, and the theories were as wild as the data itself. The first, more conventional idea involved a massive, chaotic swarm of comets. Perhaps a family of icy bodies shattered by a collision was creating a vast, uneven cloud of dust and debris that would intermittently block the star's light. While this could potentially explain the irregular dips, many scientists found it unsatisfying. The scale required is almost unimaginably large, and it does not neatly account for the long-term dimming observed over a century. This is where the most famous and speculative theory emerged, the one that captured the public's imagination. Could we be witnessing the construction of an alien megastructure? The concept, known as a Dyson sphere, involves an advanced civilization building a vast array of energy collecting panels or satellites around their star to harness its entire power output. Such a structure, incomplete and under construction, would indeed create the kind of bizarre, non-repeating light curves we see from Tabby's star. It is a breathtaking possibility, turning a data anomaly into a potential signpost of intelligence far beyond our own. Later observations have since cast doubt on this extraordinary idea. Detailed analysis of the starlight during its dimming periods showed that the light was being blocked more at some wavelengths than others, a strong indication that the obscuring material is ordinary dust, not solid panels of an alien power station. Dust scatters and absorbs blue light more effectively than red light, and that is precisely the signature telescopes detected. So the mystery seems to have a more natural, if still bizarre, answer. Yet the case is far from closed. We are still left with the fundamental question: what is creating this immense, unpredictable cloud of dust? The latest findings have not identified a single satisfactory cause. The dust behaves unlike any known circumstellar disk, and its irregular distribution remains a profound puzzle. Tabby's star stands as a powerful lesson in cosmic humility, a reminder that nature is often stranger than our wildest fiction, and that the most compelling mysteries are not always solved by finding aliens, but by discovering phenomena we simply do not yet understand. Far out in the solar system, whirling above the cloud tops of a gas giant, a geometric marvel defies the very nature of storms. At Saturn's North Pole, a perfect, colossal hexagon has been etched into the atmosphere, a six-sided jet stream wider than two Earths placed side by side. This is not a fleeting cloud formation. It is a persistent, towering structure of winds, with each of its six nearly straight sides stretching over 8,000 miles long, a feature that has endured for decades, perhaps even centuries. While hurricanes on Earth are circular vortices, this is something entirely different, a polygon of immense power and baffling stability. The hexagon acts like a permanent, rigid barrier, containing chaotic weather systems within its walls and creating a self-contained atmospheric prison. Scientists observing this phenomenon were faced with a fundamental question: how can a fluid, a gas like Saturn's atmosphere, organize itself into such a sharp-edged geometric shape and hold that form for so long? The quest for an answer moved from the rings of Saturn to spinning tanks of fluid in laboratories on Earth. Researchers created models with cylinders of water, dye, and carefully controlled rotations. They discovered that under certain conditions, when a fluid spins rapidly with different speeds at its center and its edges, it can indeed produce stable polygonal shapes, including squares, triangles, and even hexagons. This suggests the Saturn hexagon might be a kind of standing wave, a stable pattern emerging from the complex interplay of deep atmospheric currents and the planet's own rapid rotation. Yet, these laboratory analogues, while fascinating, are mere whispers of the titanic forces at work on Saturn. They cannot fully replicate the scale, the depth of the atmosphere, or the sheer energy involved. Why is it a hexagon and not an octagon or a pentagon? Why does it exist only at the North Pole, while the South Pole exhibits a more conventional, though still massive, circular vortex? The hexagon stands as a stark reminder that the laws of physics can paint with a bizarre and beautiful brush on a planetary canvas, creating patterns we are only beginning to comprehend. This atmospheric enigma, locked in ice and wind, challenges our understanding of fluid dynamics itself, proving that even the most turbulent systems can harbor pockets of perfect, impossible order. Deep within the silent tapestry of space, sudden, brilliant explosions of radio energy flare without warning. These are fast radio bursts, or FRB, cosmic gunshots that last for just a few thousandths of a second, yet in that fleeting instant they can outshine entire galaxies. The first was discovered in 2007, buried in archived data from a radio telescope in Australia, a single spike of immense power that seemed to come from nowhere. For years, it was a solitary anomaly, a mystery that some dismissed as a one-time instrumental glitch. But then more were found, and it became clear we were witnessing a genuine and deeply strange cosmic phenomenon. The central challenge with FRBs has been catching them in the act and tracing them back to a home. Their brevity makes them incredibly difficult to pinpoint, like trying to identify a single, specific camera flash in a stadium during a lightning storm. But our tools have improved. In recent years, astronomers have managed to localize some of these bursts to their host galaxies, millions or even billions of light years away. This alone was a monumental achievement, confirming they were extragalactic and immensely powerful. So what could possibly generate such a short, sharp blast of energy across such vast cosmic distances? The leading natural theories are as violent as the bursts themselves. One strong candidate is the magnetar, a type of neutron star with a magnetic field so intense it could strip the information from a credit card from halfway across the solar system. A starquake on such an object, a sudden cracking of its rigid crust, could release a titanic shockwave, rippling outwards as a colossal pulse of radio waves. Another possibility involves the cataclysmic mergers of neutron stars, collisions so energetic they ripple the fabric of space-time and forge heavy elements like gold. Yet, for all the violence of these explanations, some FRBs add another layer of mystery. Most are one-off events, but a precious few are repeaters. They flash once, go silent for days or years, and then flash again from the exact same spot in the sky. This repetitive behavior is difficult to square with a single, destructive event like a star collision. It suggests a source that can survive its own outburst, something that can power up and fire again. This resilience has inevitably led to more speculative ideas. Could we be detecting the leakage from unimaginably powerful alien propulsion systems? The energy required for an interstellar light sail, for instance, would necessitate a focused beam of radiation that, from a great distance, might look very much like a fast radio burst. While this is the least likely explanation from a scientific standpoint, it underscores just how exceptional these events truly are. They are the cosmos at its most extreme and enigmatic, brief, brilliant messages written in a language of pure energy, challenging us to decipher their origin before they vanish back into the dark. A different kind of thrust emerges not from cosmic violence, but from the quiet hum of a laboratory. The M drive, or electromagnetic drive, proposed a concept so radical it seemed to defy the universe's most fundamental rules. It was an engine with no exhaust, a rocket that promised to go nowhere. Inside a sealed, tapered metal cavity, microwaves would bounce back and forth. According to the law of conservation of momentum, for every action there must be an equal and opposite reaction. A conventional rocket pushes propellant out the back to move forward. The M drive had nothing to push against. It should have remained perfectly, utterly still. Yet when engineers tested it, their sensitive instruments registered a tiny, persistent thrust. It was a whisper of force, so small it was like the weight of a single pea resting on your palm, but it was a force where none should exist. this was not just an incremental improvement. It was a potential violation of Newton's third law of motion, the very bedrock of classical physics. If true, it would mean we could generate motion without reaction mass, opening the door to propulsion systems that could take us to the stars without carrying vast tanks of fuel. The scientific community responded with profound skepticism, as it rightly should. Extraordinary claims require extraordinary evidence, and the measured thrust was minuscule, sitting right on the edge of what instruments could reliably detect. The hunt for an error began. Could it be thermal expansion? As the device heated up from the microwaves, maybe its shape changed slightly, mimicking thrust. Perhaps it was an interaction with Earth's magnetic field, or a subtle vibrational artifact in the test apparatus itself. One particularly compelling criticism pointed to the M drive's own design. The tapered cavity, critics argued, might not be perfectly sealed from the outside universe in the way the inventors believed. The thrust could be explained by an unseen exhaust of something as simple as air molecules or even the photons of the microwaves themselves, leaking out and providing the necessary reaction mass after all. Despite these criticisms, the anomaly proved stubborn. Several independent teams, including one at NASA Eagleworks Laboratory, reported measuring a similar, inexplicable thrust under carefully controlled vacuum conditions. The results were published, peer-reviewed, and debated endlessly. The controversy became a perfect scientific storm, pitting tantalizing experimental data against the unshakable pillars of established physics. Today, the M drive stands in a kind of purgatory. No one has definitively proven it works, but no one has entirely killed the idea either. It remains a ghost in the machine of physics, a persistent hint that our understanding of momentum and the quantum vacuum might have a crack in it just wide enough for a dream to slip through. Our cosmic inventory holds another profound discrepancy, this one written in the ancient hearts of the universe's first stars. The Big Bang was not just a vast explosion of energy, it was a forge, creating the first atomic nuclei in a process called Big Bang nucleosynthesis. For the most part, our models are spectacularly successful. The calculations perfectly predict the observed cosmic abundances of hydrogen and helium, the two lightest elements. But for the third lightest element, lithium, the math falls apart. The universe should contain about 3 times more lithium-7 than we can actually find. This is the cosmological lithium problem. The predicted lithium is simply missing. How do we know this? By studying the oldest stars in our galaxy, ancient fossils whose atmospheres preserve the chemical makeup of the early cosmos. These primordial stars show a consistent, significantly lower level of lithium than our best theories of the universe's birth demand. Something is wrong with our accounting of creation's first minutes. The nuclear reaction pathways seem clear. In the hot, dense early universe, protons and neutrons fuse to form deuterium, then helium, and a small but calculable amount of lithium-7. Every variable has been checked and rechecked, from the density of the universe to the number of types of neutrinos. The equations are elegant and robust, yet they stubbornly overproduce this one element. So where did all the lithium go? One class of solutions looks inward into the stars themselves. Perhaps these ancient stars are not perfect time capsules. Could internal processes like nuclear burning or a slow mixing of material have destroyed the lithium in their atmospheres over billions of years? While some stellar models support this, the evidence is mixed, and it seems unlikely to account for the entire universal shortfall. This has led physicists to look for answers in entirely new realms of reality. Could the resolution lie in particle physics we have not yet discovered? One compelling idea involves exotic particles like supersymmetric particles or sparticles, which are predicted by theories that seek to unify all the fundamental forces. In the frantic first moments of the Big Bang, these unknown particles could have altered the nuclear reaction rates, essentially diverting the flow of fusion away from lithium production. Another radical proposal suggests that a portion of the early universe's lithium could have been transformed into heavier elements through interactions with dark matter. This idea posits that certain types of dark matter particles could have been captured by these ancient stars, sinking to their cores and annihilating, creating a slow-burning nuclear reaction that systematically destroyed lithium. This missing lithium is more than a small error in a cosmic spreadsheet. It is a direct challenge to our understanding of the universe's first nuclear furnace, a hint that the physics of the very big, the Big Bang, might be intimately connected to the physics of the very small, particles we have yet to find. The solution, when it comes, may not just fill a gap in an elemental table, but could reveal an entirely new chapter in the story of our cosmos. Even the grand tapestry of the cosmic microwave background holds a blemish that should not be there. Among the subtle variations of that ancient light, one patch stands out for its sheer extremity, a vast and profound cold spot that is statistically too large and too cold to be easily explained. It is a cosmic bruise, a region of space where the remnant heat from the Big Bang is noticeably colder than the surrounding areas. The probability of such a feature arising from random chance is incredibly low, forcing astronomers to consider that it might be a sign of something far stranger than a simple fluctuation. The most straightforward explanation proposed was a supervoid, an immense, mostly empty region of space billions of light years across. As light travels through such a cosmic underdensity, it loses energy climbing out of the void's weakened gravitational well, a phenomenon known as the integrated Sachs-Wolf effect. This energy loss would make the light appear cooler, creating a cold spot in the microwave background. The hunt began to find this hypothetical void. Yet, when astronomers mapped the large-scale structure in the direction of the cold spot, they found a void, but not nearly large or empty enough to account for the dramatic temperature drop. The observed underdensity simply does not have the gravitational punch to create the anomaly we see. With a simple explanation failing, more exotic theories have emerged from the edges of cosmology. One of the most breathtaking possibilities is that the cold spot is a scar from a collision with another universe. In the framework of the multiverse, where our universe is one bubble in a vast cosmic foam, such collisions could have occurred in the primordial chaos of inflation. The imprint of that collision, a kind of cosmic bruise on the fabric of our reality, could manifest as a vast, anomalous region like the cold spot. While this idea is highly speculative, it is a testament to just how puzzling this anomaly truly is, that scientists are willing to entertain concepts that sound like science fiction. The cold spot remains an active and tantalizing frontier of research because it refuses to conform. It is a stubborn outlier that challenges our understanding of the universe's structure and its very origins, a ghost in the machine of cosmology that whispers of a reality far wider and more wondrous than we ever supposed. Deep within the heart of matter, where the strong nuclear force binds the universe together, an impossible particle may have been glimpsed. The tetraneutron is a hypothetical and profoundly controversial object, a stable cluster of 4 neutrons and nothing else. This simple idea shatters a fundamental rule of nuclear physics. The nuclear shell model, which beautifully explains the structure of all known atomic nuclei, states that systems made purely of neutrons cannot exist in a bound state. Neutrons alone, without protons to provide balancing nuclear glue, should simply fly apart in an instant. Yet, experiments suggest this rule might have a breathtaking exception. The first tantalizing evidence emerged from particle collision experiments. Researchers fired a beam of stable atomic nuclei at a thin target. When the nuclei collided, the resulting chaos sometimes seemed to produce a resonance, a fleeting signal that looked exactly like 4 neutrons moving together as a single, coordinated unit before decaying. This was not a direct observation, but a ghost in the data, a statistical bump that implied the tetraneutron lived for just a fraction of a nanosecond. For many physicists, this was not enough. the signal was weak and alternative explanations like the chance simultaneous emission of 4 separate neutrons could not be entirely ruled out. The scientific community was deeply skeptical, as it should be when faced with something that challenges a cornerstone of theory. How could such a thing be possible? The force that holds atomic nuclei together, the strong force, is understood as acting between protons and neutrons, not between neutrons alone. The existence of a stable tetraneutron would force a complete rewrite of our models, suggesting that the nuclear force has a deeply complex, multi-body nature we have not yet grasped. It would mean that neutrons can form their own exotic states of matter, a possibility with staggering implications. Imagine the core of a neutron star, one of the densest objects in the universe. If tetraneutrons can form, could they be a fundamental building block of that incredible density, altering how we model the star's internal pressure and stability? The theoretical challenge is immense, pushing the limits of our most powerful supercomputers. Calculating the interactions between just 4 particles might sound simple, but the quantum world is a web of probabilities and forces that defies straightforward calculation. Every new experiment is a search for a clearer signal, a more unambiguous fingerprint of this nuclear phantom. The hunt for the tetraneutron is more than a quest for a new particle. It is a direct assault on our understanding of the force that builds reality itself, a tiny, fragile clue that the rules of the atomic nucleus may be far richer and more mysterious than we ever dreamed. Even the most energetic particles in the universe should have a speed limit. This theoretical boundary, known as the Greisen-Zatsepin-Kuzmin cutoff, or GZK cutoff, arises from the sheer hostility of space itself. Cosmic rays, which are mostly protons traveling at nearly the speed of light, should not be able to cross vast intergalactic distances if their energy is too high. The reason is the cosmic microwave background, that faint leftover glow from the Big Bang that fills all of space. For an ultra-high energy proton, this serene background radiation is not a gentle warmth, but a wall of high energy photons. Every single collision between such a proton and a background photon is a catastrophic event. It robs the proton of its energy, slowing it down in a process physicists call pion production. Over distances of hundreds of millions of light years, this constant grinding friction should drain these cosmic ray protons, imposing a strict upper limit on the energy we can possibly detect from distant sources. The universe, it seems, has a built-in speed bump for its most powerful particles. Yet, our observatories have seen protons that should not exist. We have detected a handful of these ultra-high energy cosmic rays, each carrying the kinetic energy of a professionally thrown baseball, but compressed into a single subatomic particle. They are rare, perhaps just 1 particle per square kilometer per century, but their existence is undeniable. These cosmic rays have energies far beyond the GZK cutoff. They have somehow run a cosmic gauntlet that should have stopped them cold, arriving at our doorstep with energies that defy the laws of physics as we understand them. How did they complete their journey without being stripped of their power? One radical explanation challenges Einstein's special relativity at its core. Perhaps Lorentz invariance, the principle that the laws of physics are the same for all observers, is not perfectly true at these extreme energies. A tiny violation could allow these protons to interact slightly differently with the background radiation, letting them slip through the cosmic dragnet that should have trapped them. This would mean our fundamental understanding of space and time is subtly incomplete. A less earth-shattering but equally puzzling idea is that these particles are not from distant galaxies at all. They must come from somewhere relatively close by within our own local supercluster of galaxies, a cosmic neighborhood where the journey is short enough to avoid the worst of the energy-draining collisions. But this only deepens the mystery because we have no known astrophysical object nearby that is capable of accelerating a single proton to such an insane energy. What local cosmic engine could possibly be this powerful, and why can we not see it? The GZK paradox is a fundamental clash between prediction and observation, a clear sign that somewhere in the chain of reasoning from the Big Bang's afterglow to the rules of relativity, we are missing a critical piece of the puzzle. The vast emptiness between stars is not truly empty, but it took a visitor from that void to prove it. In October 2017, the Pan-STARRS telescope in Hawaii detected a faint point of light moving at a speed so blistering it could only have one origin, another star system. This was Oumuamua, the first interstellar object ever observed within our solar system. Its very existence was a landmark, a piece of cosmic flotsam from a distant sun. But its behavior was what truly shattered expectations. As it tumbled away from us, astronomers rushed to collect every possible scrap of data. They found it had a shape unlike any known asteroid or comet from our own system. Its brightness varied dramatically as it spun, suggesting an extremely elongated, cigar-like form, perhaps 10 times longer than it was wide. This was bizarre, but the real shock came from its trajectory. Oumuamua was not just coasting under the sun's gravity, it was accelerating ever so slightly on its way out. For a comet, this would be normal. Icy comets heat up near the sun, venting gas and dust that acts like a natural rocket engine. But Oumuamua showed no coma, no tail, no signature of outgassing whatsoever. It was as dark and spectrally featureless as a lump of cosmic charcoal. So what was pushing it? The scientific community scrambled for answers. Could it be releasing hydrogen gas, a type of outgassing that would be invisible to our telescopes? Perhaps the pressure of sunlight itself, the gentle push of photons, was enough to explain the acceleration for an object so incredibly thin and lightweight. But each explanation felt like forcing a square peg into a round hole, requiring a series of just so conditions to fit the data. This is where the most famous and controversial hypothesis emerged. Could Oumuamua be an alien light sail? A fragment of a long-vanished civilization's technology, a solar sail so thin and light that the pressure from starlight was its primary means of propulsion. Its strange shape would be ideal for such a structure, and its lack of a visible coma or tail would be perfectly explained. It was not outgassing because it was not a comet at all, but a derelict spacecraft or a purposeful probe, silently coasting through the galactic expanse. While captivating, this idea was met with intense skepticism from the majority of astronomers. The fundamental rule of science is that extraordinary claims require extraordinary evidence, and a natural explanation, however unusual, is always more likely than an alien one. Subsequent research has leaned toward Oumuamua being a very peculiar, porous aggregate of dust and ice, a fractal-like object whose properties we simply had never encountered before. Yet, even with these more conventional theories, key mysteries remain. Its exact composition and the precise mechanism for its acceleration are still not settled. Oumuamua has since been joined by other interstellar visitors like Comet Borisov, which behaved exactly like a normal comet. This only makes Oumuamua's uniqueness stand out in sharper relief. It was our first glimpse of the building blocks of other planetary systems, and it delivered a profound lesson. The universe is capable of crafting objects that defy our current catalog, leaving behind a ghostly, tumbling enigma that continues to challenge our definitions of what is natural and what might be possible. Our most precise measurements of the cosmos are now telling two different stories about its ultimate fate. The Hubble constant, the number that describes how fast the universe is expanding today, can be measured in two primary ways. We can look at the local universe using pulsating stars called Cepheid variables as reliable distance markers. By observing these stars in nearby galaxies, we can calculate their distance and their speed of recession, giving us a present-day value for the expansion rate. This method, refined over decades, provides one very clear number. The other approach uses the cosmic microwave background, the afterglow of the Big Bang. By studying the subtle patterns in this ancient light, we can extrapolate forwards through 13.8 billion years of cosmic evolution to predict what the expansion rate should be right now. These two methods are the bedrock of modern cosmology, and they should agree. They do not. The local measurement gives a faster, more frantic expansion rate than the prediction from the early universe. This discrepancy is not a small glitch. It is a persistent and growing gap that has survived years of increasingly precise observations and intense scrutiny. Scientists call this conflict the Hubble tension. It is as if we use two different, perfectly calibrated clocks to time the same event, and one insists several seconds have passed while the other claims only one has. The difference seems small in percentage terms, but for cosmology, it is a chasm. This is not an error in our instruments. It is a fundamental mismatch between the universe's infancy and its present day, suggesting that something profound is missing from our model. What could cause this rift in our cosmic timeline? Perhaps dark energy, the force driving the acceleration, is not constant as we have assumed. Maybe it has been strengthening over time, injecting extra push into the expansion and making the modern universe speed up relative to the ancient prediction. Or the solution could lie in the realm of exotic particles. What if a new, previously unknown type of neutrino or another relic from the Big Bang is subtly altering the physics of the early universe, changing the starting point for our extrapolation? The most thrilling possibility is that the Hubble tension is our first direct evidence for physics beyond the standard model of cosmology, a crack in a beautiful but incomplete theory. Resolving this conflict may require us to rewrite the cosmic recipe itself, adding new ingredients or changing the rules of gravity on the largest scales. This isn't just a debate over a number. It is a direct challenge to our story of the universe, forcing us to ask if we have truly understood the forces that have shaped everything from the first moment to now. At the very heart of our own Milky Way, a silent, invisible storm is raging. The center of our galaxy is not just a crowded metropolis of stars, it is also a source of intense gamma-ray radiation, the most energetic form of light in the universe. When scientists analyzed years of data from the Fermi Gamma-Ray Space Telescope, they found something they did not expect. There was a clear and significant excess of this high-energy radiation, a diffuse glow emanating from the galactic core that our standard models could not fully explain. This mysterious surplus, known as the galactic center excess, has become one of the most debated puzzles in modern astrophysics. The question is simple yet profound: what is creating all this extra power? Two leading theories have emerged, each pointing to a completely different version of reality at the galaxy's core. The first and most exciting possibility is that we are seeing the indirect signature of dark matter. The leading theoretical candidates for dark matter are weakly interacting massive particles. According to this idea, when two of these particles collide, they could annihilate each other, converting their mass directly into pure energy and producing the very gamma rays that Fermi sees. The center of the galaxy is thought to have the highest density of dark matter, making it the most likely place for such annihilations to occur. Finding this signal would be a monumental breakthrough, finally giving us a window into the invisible 85% of the universe's matter. The alternative explanation is more conventional but no less fascinating. The galactic center is a chaotic, dense region packed with ancient, spinning stellar corpses known as pulsars. These ultra-dense neutron stars beam out powerful lighthouse-like pulses of radiation, including gamma rays. Could this excess simply be the combined glow of thousands of these faint, unresolved pulsars, a sort of cosmic background static from a population of objects too dim for us to see individually? The debate hinges on the intricate pattern of the light itself. If the glow is smooth and evenly distributed, it favors the dark matter explanation, as the annihilation would happen throughout the diffuse halo. If, however, the emission is clumpy, it would strongly suggest distinct point sources like a crowd of pulsars. the data so far has been tantalizingly ambiguous. Some analyses point to a lumpy structure supporting the pulsar idea. Others argue that the data is still consistent with a smooth signal, keeping the dark matter hope alive. This is not just an academic argument, it cuts to the very heart of how we understand the universe. Is the galactic center showing us the first faint whisper of dark matter, or is it simply reminding us of the incredible complexity and hidden populations of stellar objects we have yet to catalog? The answer lies in teasing apart a faint signal from an immense background, a painstaking process that continues to this day as we stare into the brilliant, mysterious heart of our own cosmic home. Far beyond the orbit of Neptune lies a frozen frontier, a vast donut of icy worlds known as the Kuiper Belt. This is the solar system's attic, packed with ancient relics from its formation. But this belt of debris does not simply fade away into the emptiness of interstellar space. Instead, it comes to a jarring, abrupt end, as if someone drew a cosmic boundary line. Astronomers call this the Kuiper Belt Cliff, the number of objects beyond a distance of about 50 astronomical units, which is 50 times the distance from Earth to the Sun, plummets to almost nothing. This is deeply strange. Our models of how the solar system coalesced from a swirling disk of gas and dust predict a much more gradual decline, a gentle tapering off of material. Finding this stark cliff is like exploring a beach and discovering the sand just stops at a perfectly straight edge. It should not be there, so what carved this edge into the frozen depths of our solar system? One of the most compelling theories points to the gravitational hand of an unseen giant. The hypothetical planet 9, a world perhaps 10 times the mass of Earth, is suspected to orbit far out in the darkness. The gravitational pull of such a massive object could have shepherded the Kuiper Belt objects, clearing out a vast region beyond its own orbit. Think of it like a cosmic shepherd, its gravity kicking smaller objects away, either sending them inward or flinging them out of the solar system entirely, leaving behind a stark, empty zone. This would elegantly explain not only the cliff but also the peculiar, clustered orbits of some distant objects that seem to be herded by an unseen force. However, a different, more dramatic story is also possible. Perhaps our sun had a close encounter with another star in its long-forgotten youth, billions of years ago when it was still nestled in its birth cluster alongside thousands of other stellar siblings. A passing star could have swooped in, its gravity violently stripping away the outer material of our Kuiper Belt like a thief in the night, stealing a portion of our solar system's primordial inventory and leaving behind this stark cliff as the only evidence of the robbery. Each theory paints a different picture of our cosmic history. One suggests a hidden world still waiting to be found in the perpetual twilight of the outer solar system. The other speaks of a violent, dynamic past where stellar close calls were commonplace. The Kuiper Belt Cliff stands as a silent monument to a mystery at the edge of our own celestial backyard. A reminder that even the familiar architecture of our solar system holds profound secrets about its birth and its journey through the galaxy. Even our own planet holds gravitational secrets locked in the deepest ice. Far above the Arctic Ocean, satellites mapping Earth's gravity field detected a profound disturbance centered on the Lomonosov Ridge, a massive underwater mountain range that stretches across the top of the world. This is not a simple variation in the planet's pull. It is a significant and focused anomaly, a place where the force of gravity is markedly stronger than our global models predict. The ridge itself is a colossal feature, a fragment of continental crust that broke away millions of years ago, now submerged beneath the polar sea. One would expect its sheer mass to create a gravitational signature, but the observed anomaly is too intense, too concentrated. It suggests that something far denser than standard crustal rock lies hidden beneath the frozen waves, pulling down on the ocean itself and tugging at the sensitive instruments in orbit. Geophysicists have proposed two compelling, yet deeply different, explanations for this polar mystery. The first theory points to the geology of the ridge itself. Perhaps the crust here is unusually thick and dense, a block of Earth's mantle that was uplifted and remains anchored deep below, creating a massive concentration of mass that amplifies the local gravity. Alternatively, the anomaly could be the ghost of an ancient cataclysm. When a massive asteroid strikes the Earth, it can create what is known as a mascon, a concentration of mass that warps the gravitational field. While no obvious crater aligns with the ridge, the possibility remains that a deeply buried impact structure from a distant era in Earth's history is the source of this strange pull. Investigations continue, with ships using seismic surveys to probe the deep structure of the ridge, trying to distinguish between a dense geological root and the shattered remnants of a cosmic collision. The Lomonosov Ridge anomaly is a powerful reminder that our maps are not yet complete, and that even the fundamental force of gravity, which we feel with every step, can behave in unexpectedly powerful ways in the planet's most remote and inaccessible realms. Some nebulae paint the cosmos with the soft, swirling brushes of chaos, but one structure near the edge of our galaxy creates art with a ruler and a set square. The Red Rectangle Nebula is a celestial geometry project, a cosmic canvas displaying near-perfect X-shaped spikes enclosed within a strikingly rectangular frame of glowing gas. This is not the gentle, rounded glow of a typical planetary nebula, the final sigh of a dying star. It is a sharp, angular structure that seems almost engineered, a stark contrast to the organic forms found everywhere else in the universe. The heart of this geometric wonder is a binary star system, two stars locked in a tight, aging dance. As one of these stars nears the end of its life, it expels its outer layers in powerful outflows. Normally, this creates a spherical shell of gas, but when two stars are present, their complex gravitational interplay can funnel this expelled material into two opposing cones or jets. We see these cones not from the side, but almost directly from one end, which gives the nebula its characteristic X shape. The stunning rectangular appearance is an illusion of this perspective, the sharp edges defined by the limits of these twin outflows. Yet, this explanation only deepens the central puzzle. Many binary stars create bipolar nebulae, but none possess the red rectangle's breathtaking symmetry and razor-sharp definition. Why is this structure so perfectly geometric when all others are messy and irregular? The leading theory points to a dense disk of dust and gas that orbits the central stars, a donut-shaped torus that acts like a nozzle, collimating the stellar winds into two incredibly precise and opposing jets. But what physical processes could create a nozzle so perfect that it forges this cosmic sigil? The profound symmetry suggests a stability and a balance of forces that we have yet to fully comprehend, a natural engine of extraordinary precision working in the dark. The red rectangle stands as a quiet monument to order, a reminder that even in the final, violent acts of a star's life, the universe can express itself through forms of perfect and utterly mysterious geometry. Perhaps the most radical challenge to our understanding of matter comes from a theory so strange it defies the very idea of a particle. Unparticle physics proposes a hidden sector of reality, a realm where matter does not behave as discrete, countable bits, but as a continuous, scale-invariant substance. Imagine trying to count water. You can count water molecules, but the fluid itself, the ocean, has no individual parts you can number. Unparticles would be like that, a kind of ethereal, non-particulate stuff that does not fit into our standard model. This is not merely a new particle, it is a new state of being, one that could manifest in subtle but detectable ways. In high-energy collisions at places like the Large Hadron Collider, physicists might spot the missing energy and momentum carried away by these unseen unparticles, a ghostly signature in the debris of shattered protons. The data would show an imbalance, energy that simply vanishes, suggesting it has leaked into this hidden sector. Even the cosmos itself could reveal clues. Certain astrophysical processes, like the intense cooling of neutron stars or the precise behavior of solar neutrinos, might operate at rates that are slightly off from theoretical predictions. These tiny discrepancies could be the whisper of unparticle interactions, a faint tug from this continuous form of matter influencing the behavior of the discrete particles we know. While entirely theoretical, the pursuit of unparticles represents a breathtaking frontier. It asks us to consider that the fundamental building blocks of reality might not be blocks at all, but something far more fluid and mysterious, a shadow realm of physics waiting just beyond the edge of our current understanding. Stretching across the sky are faint, colossal arches of radio light, so vast they dwarf the Milky Way itself. These are the galactic radio loops, immense and mysterious structures that form a ghostly cage around our galactic home. The most famous of these, known as Loop 1, spans over 100 degrees of the night sky, a celestial arc so enormous it would take light tens of thousands of years to travel from one end to the other. From our perspective on Earth, it appears as a giant, ethereal bubble, a shimmering wall of radio waves that hints at a violent and energetic past. The sheer scale of these loops presents an immediate puzzle. What kind of cosmic event could carve such immense structures into the interstellar medium? The most straightforward explanation points to the fury of dying stars. A supernova explosion is one of the most powerful events in the universe, and when a massive star dies, it can blow a gargantuan bubble in the surrounding gas and dust. The shockwave from such an explosion could expand for millennia, sweeping up material and energizing it to glow in radio frequencies, creating the very loops we observe. In this scenario, Loop 1 could be the ancient remnant of a single, spectacular stellar death that occurred relatively close to our solar system, its echo still visible long after the star itself has vanished. Yet, the evidence is not quite so clear. Some of these loops appear to be connected, forming a complex web of interrelated structures that a single, isolated supernova would struggle to create. This has led to an alternative, even more powerful theory. Perhaps these loops are not the scars of individual explosions, but the imprint of our galaxy's own magnetic field. The Milky Way is laced with powerful magnetic lines of force, and some scientists propose that these loops trace out vast, coherent magnetic structures like cosmic ley lines made visible. In this view, the radio emission is synchrotron radiation, generated by high-energy electrons spiraling at nearly the speed of light along these invisible magnetic pathways. The loops, then, would be windows into the fundamental skeleton of the galaxy, a hidden architecture of force that we can only see when particles dance along its lines. So which is it? The answer remains frustratingly out of reach. The data we have can be interpreted either way. The loops could be the fading bruises from ancient stellar cataclysms, or they could be the permanent, luminous veins of the galaxy's magnetic heart. Resolving this debate requires more than just radio telescopes. It demands a deeper understanding of how energy propagates through the complex and turbulent medium of interstellar space. These silent, soaring arcs remind us that our galaxy is not a static collection of stars, but a dynamic, energetic system whose history is written in colossal, invisible ink, waiting for us to learn how to read it. That vast cosmic bruise in the ancient light of creation finds a potential culprit in the darkness. Lying in the same direction as the CMB cold spot is a staggering emptiness, a region of space known as the Eridanus supervoid. This is not just a simple gap between galaxies, it is a colossal underdensity, a bubble in the cosmic web billions of light years across where the concentration of galaxies and matter is dramatically lower than the surrounding universe. It is a true cosmic desert, a place where the usual glittering cities of stars are replaced by a sparse and lonely frontier. The existence of such a void, aligned with the cold spot, seemed at first like a perfect explanation. As light from the Big Bang's afterglow travels through the universe, it must climb in and out of the gravitational wells created by matter. Passing through a supervoid is like rolling a ball up a long, gentle hill. The light loses energy struggling against the weakened gravity of this vast emptiness, and that energy loss makes it appear cooler, manifesting as a cold spot on our maps. This is the integrated Sachs-Wolf effect, a well-established prediction of cosmology. The problem is one of scale. The Eridanus supervoid, while immense, is simply not immense enough. Its gravitational pull is too weak, its hill not nearly steep enough to account for the dramatic temperature drop we observe in the cold spot. The numbers do not add up. The void would need to be far larger, far emptier to create such a profound chill, a requirement that clashes with our understanding of how structure forms in the universe. This mismatch forces a difficult question: is our standard model of cosmology, which assumes a largely uniform universe, fundamentally incomplete? The cold spot and its underwhelming void point toward a concept known as inhomogeneous cosmology. This is the idea that our place in the universe might not be entirely typical, that we could be living inside a much larger bubble of lower density than the cosmic average. In such a model, the Eridanus supervoid would not be a lone anomaly, but part of a grander, lumpier structure that our current surveys have not yet fully mapped. The cold spot would then be a consequence of this larger-scale unevenness, a sign that the smooth, uniform cosmos we use in our equations is an oversimplification of a far more complex and textured reality. This possibility shakes the foundations of cosmology, suggesting that the forces shaping the universe's expansion might work differently on the very largest scales, in realms of emptiness we are only beginning to perceive. Our entire understanding of physics rests on a foundation of unshakable numbers, the fundamental constants that dictate the strength of forces and the behavior of matter. We have always assumed these values are fixed, eternal pillars of reality, the same everywhere and for all time. Yet, a series of extraordinary observations now suggests that these pillars might be slowly, subtly shifting. This is the deeply controversial evidence for varying fundamental constants, a finding that would force us to rewrite the laws of physics from the ground up. The key to this mystery lies in the light from the most distant objects in the universe, quasars. As their brilliant light travels for billions of years to reach us, it passes through ancient clouds of interstellar gas. These clouds act like cosmic fingerprints, absorbing specific colors from the quasar's light and leaving behind dark lines in its spectrum. The precise positions of these lines are dictated by the fine structure constant, a number that governs the strength of the electromagnetic force. It controls how atoms hold together and how light interacts with matter. When scientists analyzed these ancient absorption lines, they found something astonishing. The lines were not quite where they should be. The implication was staggering. Billions of years ago, in those faraway gas clouds, the fine structure constant was slightly different. It was smaller than it is today. The electromagnetic force was subtly weaker in the early universe. The statistical significance of this result has been fiercely debated for years. Could it be an artifact of the incredibly complex measurements? Perhaps unknown systematic errors in the telescopes or in our models of these distant clouds are creating a phantom signal. The team behind the discovery has checked and rechecked their work, and the anomaly persists. If this variation is real, its consequences are almost beyond comprehension. The fine structure constant is woven into the very fabric of reality. A change in its value would mean that the laws of chemistry and atomic physics were different in the past. The nuclear reactions that power stars, the very formation of carbon and oxygen in stellar furnaces, all depend critically on this number. If it were even a few percent different, the universe could be devoid of the complex chemistry necessary for life. This leads to a profound and unsettling question. Are we living in a universe whose laws are uniquely tuned for our existence, or are those laws themselves slowly evolving? The idea of varying constants is not entirely new. Some theories, like string theory, actually predict the existence of additional spatial dimensions that could slowly unfurl over cosmic time, causing what we perceive as constants to gradually change. The hunt for confirmation is now underway, using everything from atomic clocks in laboratories to the precise timing of pulsars in our galaxy. They are all searching for the same thing, a tiny, telltale drift in the tick of the universe itself. The constancy of our constants is the bedrock of all modern science, but that bedrock may now be showing its first hairline cracks, revealing a cosmos that is far more dynamic and unpredictable than we ever dared to believe. From the faint, unaccounted-for tug on our deepest space probes to the accelerating expansion of the cosmos itself, these 25 anomalies form a constellation of cosmic uncertainty. They are not failures of our science, but its ultimate drivers, each one a brilliant question mark pushing at the boundaries of our understanding. The Pioneer Anomaly's gentle deceleration, the impossible speed of galaxy rotation pointing to dark matter, the eerie alignment of the cosmic axis, and the fleeting brilliance of the wow signal all whisper the same profound truth. There is so much more to the universe than we have yet dared to dream. Even our most fundamental constants may not be constant, and the void itself may hold structures we can barely perceive. These puzzles remind us that every answer we uncover simply reveals a deeper, more fascinating layer of mystery. So as we look up at the silent, star-filled night, one question remains: what other breathtaking secrets are waiting in the vast, dark expanse just beyond the edge of our current vision? Which of these 25 cosmic riddles captured your imagination the most? Let us know in the comments below, and subscribe to continue unraveling the greatest mysteries of space and time together.